Functions of the Sun, How Heat and Light Are Produced, and What It Means in Our Lives, by Victoria Bailey, Regents Online through Columbia State. The world runs off of energy. We think of energy as what powers our cars, our electronics, and our appliances. But energy is actually all around us at all times. It's what powers our bodies. It's what powers the cells within our bodies. Without energy, we wouldn't be able to walk, talk, or even live. Energy is the very thing that all of life on Earth subsists of. From people, to animals, to even plants. But where does this energy come from? And why is it so important? It can all be explained by the sun. But how does this energy that powers everything around us come into being? This can be explained through something called the conservation of energy. The law of conservation of energy states that no energy within a system can be created or destroyed, although it may change forms. So the world acts like a giant generator, in which energy is constantly being cycled, recycled, and reused. When discussing the conservation of energy and the energy cycle in terms of the sun, an example would be that the sun's light nurtures plants and gives them energy. The animals then eat these plants and absorb their energy. Humans eat both plants and animals to absorb the energy that they hold. The humans then release the energy in the form of heat and waste. Without the sun, there would be no life on Earth. This is because the sun's warmth enables plants to grow and nourishes them, which creates energy. With no plants, there would be no energy sources for people or animals to subsist on, and human and animal life would quickly disappear. But a lack of plants is not the only reason why the sun is important to life on Earth. Even if humanity could find a way to produce vegetation, a lack of heat would be deadly. Without the sun, within a week, the average global surface temperature would drop below 0 Fahrenheit. In a year, it would dip to negative 100 degrees. The top layers of the ocean would freeze over, but in an apocalyptic irony, that ice would insulate the deep waters below and prevent the oceans from freezing solid for hundreds of thousands of years. Millions of years after that, our planet would reach a stable negative 400. Obviously, the sun is very important to our survival. But why? Understanding how the sun works is vitally important in understanding how it affects our survival. Once viewed by scientists as simply a giant ball of fire or ball of flame, the sun is now understood to be an object with complex physical and chemical processes. The sun contains mostly hydrogen and releases energy by nuclear interactions between the hydrogen atoms. A nuclear reaction is a less typical reaction. While the outside of atoms interact in most common chemical reactions, a nuclear reaction works a little differently. During a nuclear reaction, the nuclei of the atoms interact instead of the surface of the atoms. Because of this, these kinds of reactions take much more initial energy to effectively reach threshold level and trigger a reaction. However, they also release an incredible amount of energy when they are triggered. The sun's core is incredibly hot, and at these extreme temperatures, the hydrogen atoms rip apart and an enormous amount of energy is released by each atom. When these atoms are ripped apart, they separate into hydrogen nuclei and negatively charged electrons. The hydrogen nucleus is a positively charged proton. Hydrogen nucleuses account for 91% of the atoms in the sun. As all of these chemical reactions take place, positively charged protons are created, which then combine to create neutrons. This process takes an extreme amount of energy, which is created by pressure and heat. Next, helium is created from hydrogen with the creation of a deuteron. Then a proton collides with this deuteron to create a helium-3 nucleus. Finally, two helium-3 atoms collide and create a helium-4 atom. The changes in energy and atomic structure create fusion reactions, which create incredible amounts of heat and light as positively charged protons collide with negative electrons and create huge releases of energy in the form of both heat and light. Scientists believe this process of fusion reactions begin when the nebula, a huge cloud of particles and gas, collapse under its own force due to gravity. These fusions, which happen at the center of the sun, must make it through several layers of the sun before they actually escape into the atmosphere. As this massive amount of energy are created in the core of the sun, the energy is passed through the layers of sun outward and into the atmosphere in the form of kinetic energy charged particles. Layers of the sun. First layer. The first layer of the sun is the radiative layer. The temperature drops rapidly through this layer, which is the closest layer to the core, going from nearly 1,000,000 Kelvin to roughly 2,000,000 Kelvin. It is shifted through this layer by process of radiation. Layers of the sun. Second layer. The second layer is the convective layer. The convective layer of the sun is the sun's outer layer. The temperature is even lower here, and the effectiveness of using radiation to move particles is unsubstantial. Rising thermal cells instead carry the heat towards the sun's surface. As these cells reach the surface, they release the heat they carry and become heavy as they cool, at which point they sink back towards the radiative layer of the sun, and the cycle is allowed to continue. Layers of the sun. Third layer. The last layer of the sun is the surface area, called the photosphere. This is the visible layer of the sun. The photosphere is tens to hundreds of kilometers thick and 4,500 to 6,000 kelvins in temperature. The energy, which was transferred from the core of the sun through the radiative layer and the convective layer, is propagated out into the surface as it reaches the photosphere of the sun. How light travels through the atmosphere. Because the atmosphere in open space limits the use of convection or conduction in regards to the travel of light and heat, the heat is moved away from the sun through the use of radiation. This radiation is very strong and is capable of sending out extremely intense and deadly levels of ultraviolet rays of light. Although most of the radiation the sun emits is in the form of visible light, the small amount of ultraviolet and infrared rays that it creates is capable of being extremely dangerous. Ultraviolet light is high-energy light with very short wavelengths. These ultra-powerful UV rays can actually cause the molecules of whatever substance they strike to vibrate with such speed and intensity that they can knock electrons away from atoms and cause the splitting of atoms. This splitting of atoms within a substance can cause damage, deformity, and changes within the substance's DNA, which would be extremely deadly to any living creature on Earth. Thankfully, before reaching Earth, the radiation carried energy of the sun must pass through something called the ozone layer. The ozone layer is a molecule composed of 3 oxygen atoms. This layer of the Earth's atmosphere is called the stratosphere and is only about 10 to 50 kilometers above the Earth's surface. When the ultraviolet rays collide with the ozone layer, most are kept from penetrating through the atmosphere and reaching the surface of the Earth and the living creatures who inhabit it. Without the many different chemical and physical processes that take place to ensure that heat and light in the form of visible light and life-sustaining amounts of heat and radiation actually reached our bodies and the atmosphere, there would be no conceivable way that life as we know it would be possible on Earth. Without the sun, there would be no vegetation for the energy life needs on a daily basis for survival, and the Earth would grow far too cold to sustain life. Our beautiful and delicate ecosystem is daily kept in check by billions of chemical reactions that are taking place around us at all times. None so important as those that create, maintain, and filter heat and light into our ecosystem, without which our survival would be impossible. My references for this paper and accompanying PowerPoint are a public outreach module, Sunlight and Solar Heat, How Are They Made, in genesis.gov. Does heat travel differently in space, in Northwestern EDU? My references for this paper and accompanying PowerPoint are If the Sun Went Out, How Long Could Life on Earth Survive? In Popsy.com by H. Otterbein. Ultraviolet Radiation in Biospherical.com, How Does the Sun Produce Energy in UniverseToday.com by M. Williams, and The Law of Conservation of Energy in ExplainThatStuff.com by C. Woodford.